states that the length of a pin is twice its width plus 3 feet. This gives us a system of two equations in two variables. Solving this system using the elimination method, we first rewrite the second equation so that both equations are in standard form. We can now eliminate either variable L or W by choosing an appropriate multiplier for the second equation before adding the equations. If we choose to eliminate the variable W, we multiply the second equation by 3. When we add the equations, the W terms disappear, or equals 27. We can then substitute this value into either of the original equations to find the value for W. Calculate the sum. And completing the arithmetic, we get negative 2W equals negative 20. So this problem containing two unknowns can be solved by creating a single equation with a single variable expressing both unknowns in terms of that one variable. Or we can solve the problem by creating a system of two equations in two variables where each unknown is represented by a different variable. Now let's look at another example from the lecture Solving Motion Problems with Linear Equations. In this problem, a car and a bus are each traveling at constant speeds in opposite directions on a highway. 3 hours after they pass each other, they are 360 miles apart. If the car is traveling 10 miles per hour faster than the bus, how fast is each vehicle traveling? We solved this problem by creating a single equation with a single variable s, which represented the speed of the bus. We then represented the speed of the car as s plus 10, since the car's speed is 10 miles per hour faster than the bus. We know that both vehicles traveled for 3 hours. So knowing that speed times time equals distance, we wrote expressions for the distance traveled by each vehicle. In 3 hours, the bus traveled 3s miles, and the car traveled 3 times s plus 10 miles. Since the sum of these distances must equal the distance between the two vehicles, or 360 miles, we could then create a single equation which can be solved to find the value of s. Solving this equation, we get s equals 55, which tells us that the bus's speed is 55 miles per hour, and the car's speed is 55 plus 10, or 65 miles per hour. So just as in the previous example, we were able to express both unknowns in terms of a single variable and write expressions for the distances traveled by each vehicle using only that one variable. These expressions were then combined to create a single equation. But once again, this problem can also be solved by creating a system of two equations in two variables. To do this, we assign the variables s and r to represent the speeds of the bus and the car. Since distance is equal to speed times time, the distances traveled for the bus and the car are 3s miles and 3r miles. We can then create two equations, each of which states one relationship between the variables. The first equation states that the distance traveled by the car plus the distance traveled by the bus is equal to 360 miles. The second equation states that the speed of the car is 10 miles per hour faster than the speed of the bus. This gives us a system of two equations in two variables. Solving this system using the elimination method, we first rewrite the second equation so that both equations are in standard form. If we choose to eliminate s, we multiply the second equation by 3. Equations, giving us the equation 6 to this value. Since the bottom equation is the simpler of the two, we will use it to calculate the value of s. Subtracting 65 from both sides eliminates this term on the left. And completing the arithmetic, we get negative s equals negative 55, or s equals 55. So this problem containing two unknowns can be solved by creating a single equation with a single variable, expressing both unknowns in terms of that one variable. Or we can solve this problem by creating a system of two equations in two variables, where each unknown is represented by a different variable. The method which is easiest depends upon the problem. The two examples which we have seen so far could be solved using either method with similar difficulty. However, in some cases, creating a system of equations is clearly the easier method. For example, let's solve a problem involving different combinations of items which cost different prices. John, Denny, Michelle, and Cass go to a movie. They spend $69 on 4 movie tickets and 3 drinks. But Roger, David, Chris, Jean, and Michael are also going to see the same movie. And they spend $88 on 5 movie tickets and 4 drinks. So given the information that 4 tickets plus 3 drinks cost $69, and 5 tickets plus 4 drinks cost $88, is it possible to calculate the pricing at the theater for tickets and drinks? Solving this problem by creating a system of equations is straightforward. If we let t represent the price of a ticket, and d represent the price of a drink, we can easily create a system of two equations in two variables t and d. We can then use the elimination method to eliminate a variable. For instance, if we wish to eliminate the d terms, we multiply the top equation by 4 and the bottom equation by negative 3. Completing the arithmetic, we then add the equations which eliminates the variable d, leaving us with the equation t equals 12. We can then substitute this value into either of the original equations to find the value of d. Since the top equation has the smallest coefficients, we will use it to calculate the value of d. Subtracting 48 from both sides eliminates this term on the left. And completing the arithmetic, we get 3d equals 21, or d equals 7. Since d represents the price of a drink, and tickets cost $12 each, we would have to write one unknown, either the price of tickets or drinks, in terms of the other, so that one of the variables can be eliminated. So let's say we rewrite the first equation so that the price of a ticket is written in terms of the price of a drink. This expression for the price of a ticket could then be substituted into the second equation to eliminate the price of a ticket from that equation. This gives us a single equation with one unknown, the price of a drink, which can be represented with a single variable d. But all we have done is to eliminate one of the variables through substitution. This was basically no different than solving the system of two equations in two variables using the substitution method. But what if instead of two groups of people who buy tickets and drinks, there are three groups of people who buy tickets, drinks, and popcorn? This problem now has three unknowns: the price of a ticket, the price of a drink, and the price of popcorn, which we could represent by three variables: t, d, and p. This problem would be very difficult to set up using a single equation with one variable. However, the solution can be calculated in a straightforward manner by using a system of three equations in three variables. In the next several lectures, we will introduce methods of solving systems such as these, and see how systems of linear equations in three variables can be visualized in three-dimensional space. Hawk, and welcome to YU. In the last several lectures, we studied systems of two linear equations in two variables and saw how these systems could be represented graphically as lines in the Cartesian plane. Systems of equations can consist of more than two equations, and the equations in the system can contain more than two variables. In this lecture, we will introduce systems of three linear equations in three variables and see how they can be visualized in three-dimensional Cartesian space. The standard form of a linear equation in x and y is written as ax plus by equals c, where a, b, and c are constants, and at least one of the coefficients a or b must be non-zero. The term linear reflects the fact that the graph of an equation of this form will be a straight line in the xy plane. Just as the standard form linear equation in two variables x and y is written as ax plus by equals c, a standard form linear equation in three variables x, y, and z is written as ax plus by plus cz equals d, where at least one of the coefficients a, b, or c must be non-zero. Since the equation contains three variables, it must be graphed using a three-dimensional coordinate system, as we saw in the lecture Cartesian coordinates in 3 dimensions. So what does the graph of a linear equation in three variables look like? Let's start by looking at some simple examples in two variables and then extend the examples to three variables. When a linear equation is written in standard form, setting the coefficient of any variable to 0 causes the term containing that variable to disappear. Even though that variable is no longer included in the equation, it is understood that the variable still exists and is free to take on any value. This is why in a standard form linear equation, a and b cannot both be 0, since this would eliminate both variables from the equation. If in fact the constant c was 0, then x and y could take on any value and the statement would still be true. The solution set would therefore contain every possible combination of x and y. And if the constant c was not 0, then no values of x and y would make the statement true, and the solution set would therefore be the empty set. Since in either case, the graph of the solution set would not be a line, the equation 0 equals c cannot be a linear equation. So let's create a simple linear equation in x and y by setting a to 0 and b to 1. This eliminates x from the equation. If we set the constant c to 3, we get the linear equation y equals 3. Since the values of x are no longer constrained by the equation, x is free to take on any value. The graph of this equation therefore consists of every point whose y-coordinate is 3 and x-coordinate is any real number. The set of all these points is a horizontal line 3 units above the origin. Likewise, setting b to 0 and a to 1 eliminates y from the equation. If once again we set c to 3, we get the linear equation x equals 3. Now, since y is free to take on any value, the graph of this equation consists of every point whose x-coordinate is 3 and y-coordinate is any real number. The graph of this equation is therefore a vertical line 3 units to the right of the origin. Now let's try the same thing for a linear equation in 3 variables, setting the coefficients of all but one of the variables to 0. Let's start by setting a and b to 0 and c to 1. This eliminates all the variables but z. If we set the value of d to 3, we get the linear equation z equals 3. Since both x and y are free to take on any value, the graph of this equation consists of every point in 3-dimensional space whose z-coordinate is 3 and x and y coordinates are any real number. The graph of this equation is therefore a horizontal plane 3 units above the origin. If we set a and c to 0 and b to 1, all variables but y are eliminated from the equation. And setting d to 3, we get the equation y equals 3. Now, since x and z are free to take on any value, the graph of this equation consists of every point whose y-coordinate is 3. The graph of this equation is therefore a vertical plane, 3 units to the right of the origin. Likewise, if we set a, b, c, and d to 1, 0, 0, and 3, all variables but x are eliminated, giving us a graph which consists of all points with an x-coordinate of 3. The graph of this equation is a vertical plane 3 units in front of the origin. Now, what do you suppose would happen if we set the coefficient of only one of the 3 variables to 0? For example, let's set the z coefficient to 0 and the x and y coefficients to 1. This eliminates z from the equation, but leaves the variables x and y. Now, if we set the value of d to 3, we get the linear equation x plus y equals 3. Let's ignore z for the moment and plot this equation on the xy plane. This gives us a line which intersects the x and y axes. Every point on this line is a solution to the equation x plus y equals 3, where the z-coordinate of every point is 0. But there are more solutions than this. All points on any line where x plus y equals 3 are solutions to this equation regardless of the value of z. There are an infinite number of lines like this, one line for every possible value of z. Since z can be any real number, all these lines together create a plane. Each point in this plane corresponds to a solution of the linear equation x plus y equals 3. The graph of a linear equation in 3 variables will always be a plane when graphed in Cartesian coordinates, assuming that the constants a, b, and c are not all 0. Any plane which corresponds to the solutions extends infinitely in all directions. Depending upon the values of a, b, c, and d, the plane may lie in any position and orientation. We have seen that systems of 2 linear equations in 2 variables can be represented graphically as lines in the Cartesian plane, and the solutions of these systems correspond to the points where the lines intersect. In systems of 3 linear equations in 3 variables, the equations are represented as planes in Cartesian space. Each plane may be oriented at any angle and positioned anywhere in space relative to the other planes. Since each plane graphically represents the set of solutions to one of the 3 equations, the points where all 3 planes simultaneously intersect correspond to the solutions which simultaneously satisfy all 3 equations. These points therefore correspond to the solutions of the system. In the next lecture, we will look at different ways in which 3 planes can intersect in 3-dimensional space, and thus different types of solutions which can exist for a system of 3 linear equations in 3 variables. Schmohawk, and welcome to YU. In the last lecture, we saw that just as the graph of a linear equation in 2 variables creates a line which extends infinitely in both directions, the graph of a linear equation in 3 variables creates a plane which extends infinitely in all directions. Since the graph of a linear equation in 3 variables is a plane, a system of 3 linear equations in 3 variables can be represented as a group of 3 planes. Each plane may be oriented at any angle and positioned anywhere in space relative to the other planes. Since each plane represents the set of solutions to one of the 3 equations, any point which simultaneously falls on all 3 planes corresponds to a solution which simultaneously satisfies all 3 equations. That point will therefore be a solution of the system. In this lecture, we will look at different ways in which 3 planes can be oriented in 3-dimensional space, and different types of solutions which can exist for a system of 3 linear equations in 3 variables. We saw that systems of 2 linear equations in 2 variables can have 3 types of solution sets, depending upon the ways in which the lines are oriented in the Cartesian plane. If the lines have different slopes, then they must intersect at a single point, and the system will have a single unique solution. If the lines are distinct and parallel, then there are no points of intersection, and the system has no solutions. And if the lines are identical, the 2 graphs coincide, intersecting at an infinite number of points. The system therefore has an infinite number of solutions. Likewise, systems of 3 linear equations in 3 variables can have a single unique solution, no solutions, or an infinite number of solutions, depending on the ways in which the 3 planes are oriented. Let's consider all the possible ways in which three planes can intersect or not intersect. We will number these planes 1, 2, and 3. One possibility is that no two planes in the system are parallel, and all three planes intersect at only one point. In this case, the system will have one unique solution. A second possibility is that two of the planes are not parallel, and so their points of intersection form a line. If the third plane intersects the other two along this same line, then the common points of intersection for all three planes are represented by that line. The system for all intersects the intersection is that two of the planes are not parallel, and so their points of intersection form a line. If the third plane intersects the other two along this same line, then the common points of intersection for all three planes are represented by that line. The system will therefore have an infinite number of solutions corresponding to every point on the line. The third plane does not necessarily have to be distinct from both of the other planes. If the third plane is identical to one of the other two planes, then the points common to all three planes are still represented by the same line of intersection, and the system will have an infinite number of solutions. An infinite number of solutions will also exist if a system consists of three identical planes. In this case, any point which lies on one plane is common to all three planes. The system will therefore have an infinite number of solutions corresponding to every point on the plane. In addition, there are several orientations of the planes which will result in a system with no solutions. Anytime a system has two distinct parallel planes, there can be no solution. Since distinct parallel planes have no points in common, regardless of the orientation of the third plane, there can be no points which lie on all three planes. The third plane can be distinct and parallel to the other two, identical to one of the other two, or not parallel to either of the other planes, thus intersecting both planes. Regardless of the orientation of the third plane, since there are no points in common to all three planes, the system has no solutions. One additional configuration of the planes which will result in a system with no solutions is if the planes are oriented so that their intersection points lie along three distinct parallel lines. Once again, since there are no points in common to all three planes, so that their intersection points lie along three distinct additional configuration of the planes which will result in a system with no solutions is if the planes are oriented so that their intersection points lie along three distinct parallel lines. Once again, since there are no points in common to all three planes, the system has no solutions. So we have seen 8 ways in which the three planes in a system of 3 linear equations in 3 variables can be oriented. These orientations can create a system with one solution, an infinite number of solutions, or no solutions. These are the same 3 general categories of solutions which can exist for systems of 2 linear equations in 2 variables. Systems in 2 variables have a single unique solution when the 2 lines in the system are not parallel and thus intersect at a single point. Likewise, systems in 3 variables have a unique solution when none of the 3 planes are parallel and intersect at a single point. Systems in 2 variables have no solutions when the 2 lines are parallel and distinct. And systems in 3 variables have no solutions when any 2 planes are parallel and distinct, or when the planes are oriented so that their intersection points lie along 3 distinct parallel lines. An infinite number of solutions exist for systems in 2 variables when the 2 lines coincide number of distinct, or when the planes are lines. An infinite number of solutions intersecting or intersect along a line. Or intersect along a line. Regardless of the number of variables or equations in a system, if the system has one or more solutions, it is called consistent. And if the system has no solutions, it is inconsistent. Likewise, 2 or more equations whose graphs are identical are called dependent, and equations with distinct graphs are independent. Now that we have seen how systems of 3 linear equations in 3 variables can be visualized, in the next lecture we will see how these systems can be solved.